Hello there and welcome to the Sleepy Space Channel. There is a cliff on one of the moons of Uranus that would take 12 minutes to fall down. Nobody can tell you exactly how tall it is, because the only spacecraft that ever went there passed once, 4 decades ago, and never came back. It also arrived in the wrong season. Half of every moon in that system was sitting in a night that lasts 42 years, and that half has never been photographed at all. Tonight we work through what the sunlit half contained: banded terrain nothing else in the solar system resembles, valleys that appear to have been flooded from below, and a small moon that may once have held an ocean filling half its volume. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. Those worlds have waited 4.5 billion years, and they can wait a little longer. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The system that lies on its side. Everything strange about the moons of Uranus begins with the orientation of the planet they belong to. Uranus is tipped roughly 98 degrees away from the plane of its orbit. That is not a lean. That is a world lying on its side. The other planets spin like tops, with their poles pointing up and down relative to the path they travel. Uranus rolls. Its equator runs nearly vertical to the direction of the sun, and its poles take turns pointing almost directly at it. Whatever produced that condition happened early, and it happened to the entire system at once. The 5 major moons inherited the tilt completely. Regular satellites form in a disk around a planet's equator, and they stay locked to that plane long after the disk itself is gone. So the moons of Uranus do not circle the planet's waist in the way our own moon circles Earth. They circle a ring that faces the inner solar system almost head-on for half of the Uranian year. Seen from a great distance, the system does not look like a spinning plate turned edge-on. It looks like a target. The planet sits at the center, and the moons are drawn around it in concentric rings, like circles painted on a board. That single geometric fact governs almost everything that follows. It governs the light. It governs the seasons. It governs where the frost goes and where it does not. And it governs, in a way that is quietly severe, how much of these worlds we have ever been able to see. Uranus takes about 84 Earth years to complete one circuit of the Sun. Divide that into 4 seasons, and each one runs for roughly 21 years. Each pole spends about 21 years leaning toward the Sun, then about 21 years leaning away from it. In practical terms, any given hemisphere on any given moon receives something close to 42 continuous years of dim daylight, followed by something close to 42 continuous years of unbroken night. There is no dawn on a timescale that a human being would recognize as a dawn. A person standing at high latitude on one of these moons could live an entire working life inside a single long twilight, and would have to survive an equally long darkness before the sun came back. There are 29 known moons in the system, and the number has grown by increments as instruments improved, rather than in any single burst of discovery. Most of them are small. Some are dark, irregular shards, threading through the narrow ring system close to the planet, shepherding the ring edges and being ground down by collisions over time. Others are distant, captured objects, far out, many of them traveling backwards relative to the planet's rotation, almost certainly not native to the system at all. Only 5 of them are large enough to matter geologically. Only 5 have pulled themselves into round shapes under their own gravity, and only 5 carry a surface history worth reading. In order outward from the planet, they are Miranda, Ariel, Umbriel, Titania, and Oberon. Their names are the one part of this system that has nothing to do with physics. Uniquely among the planets, the moons of Uranus are not named from classical mythology. They take their names from English literature, from Shakespeare, and from Pope, which is why the roll call reads like a caste list rather than a pantheon. Miranda comes from the island in The Tempest. Ariel from the same play. Titania and Oberon from A Midsummer Night's Dream. Umbriel from a poem about a stolen lock of hair. The tradition began early and it stuck, and it has quietly shaped how these worlds sound to us ever since. They are also small. Titania, the largest, is roughly 1,578 kilometers across. That makes it the 8th largest moon in the solar system, which sounds impressive until you set it beside our own moon, which is more than twice as wide. Oberon follows closely at about 1,523 kilometers. Ariel and Umbriel are near enough to identical in size that the difference between them is a matter of a few kilometers, both sitting a little over 1,100 kilometers across. And Miranda, the innermost of the 5, is only about 470 kilometers from side to side. You could drive around it in a couple of days, if there were anywhere to drive. Add all 5 together, and their combined mass comes to roughly 1/8 of the mass of Earth's moon. That is the context for everything that comes later in this account. These are small worlds. They are cold, they are lightweight, they hold very little heat, and by every reasonable expectation, they should be geologically finished. Bodies of this size are supposed to be simple. They form, they are battered by impacts for a few 100 million years, they freeze through, and then they wait. That is the standard story for small icy moons, and it is usually correct. It is not correct here, and that is the difficulty. Their orbits are tidy and closely spaced. Miranda circles the planet in about 1.5 days, at a distance of roughly 130,000 kilometers from the planet's center. Ariel takes about 2.5 days. Umbriel about 4. Titania about 8.75 days, and Oberon, farthest of the 5, takes about 13.5 days at a distance of some 580,000 kilometers. All 5 are tidally locked, which means each one keeps the same face permanently turned toward the planet. From any spot on any of these moons, Uranus does not rise and does not set. It simply hangs where it is. Their densities cluster in a narrow band, somewhere between about 1 2/10 and 1 7/10 grams per cubic centimeter. That is a useful number because it tells you what they are made of without ever landing on them. A density in that range means roughly half water ice and roughly half rock, mixed through the body rather than layered as a rocky world with a frosting of ice on top. These are ice worlds in the full sense, not rocky worlds wearing ice. The planet they orbit turns quickly for something so large, completing a rotation in about 17 hours and 14 minutes, and it turns backwards relative to most of the solar system. That too is a consequence of the same great tipping. Around the planet lie 13 known rings, narrow and startlingly dark. They are nothing like the bright ice of Saturn. They are closer to charcoal, thin ribbons of very dark material, difficult to see and easy to miss. And around all of it, sunlight arrives at roughly 1/400th of the intensity it has at Earth. That does not mean darkness, exactly, but it does mean that the entire system operates in what a human eye would read as permanent, deep twilight. The sun there is not a disk. It is a point of light, brilliant and small, casting hard black shadows across surfaces that have not been warm in 4.5 billion years. the tilt itself has never been fully explained, and the explanations on offer are worth holding in mind. The leading one proposes a collision, or a series of collisions, with a body of substantial size early in the planet's history, striking hard enough to knock the whole world over. A competing idea holds that a large satellite, long since lost, exerted a slow gravitational torque over a very long period and walked the axis around by degrees. Both accounts share an important implication. If the planet was struck hard enough to be tipped, the moons that existed at the time would not have survived intact. The 5 we see may have reformed afterwards, out of a disk of debris left behind by the impact. In that reading, these are second-generation worlds, built from the wreckage of whatever came first. There is one more detail worth carrying forward. The innermost small moons are packed so tightly together that their orbits are not stable over long periods. Models suggest that region is rearranging itself even now, on timescales of millions of years, with moons perturbing one another, crossing paths, and occasionally colliding. The system is not a finished object sitting quietly in the dark. It is still settling. That is the frame. A planet lying on its side, dragging 5 round worlds and 24 smaller ones around with it, each of them locked into a rhythm of 42 years of light and 42 years of darkness, all of it turning slowly through a twilight that never brightens. It is an orderly arrangement, and a very old one. What makes it worth an entire night of attention is not the arrangement. It is what happened when we finally sent something out there to look, and how little of it we managed to see. Part 2. 1 week of looking. Almost everything humanity knows about the surfaces of these 5 worlds was gathered during a single flyby by one spacecraft on one pass 4 decades ago. There has never been an orbiter at Uranus. There has never been a second visit. There has never been a lander, a probe, a return, or even a distant follow-up mission that came close enough to resolve a mountain. The entire photographic record of 5 planet-sized geological systems comes from a few hours of close approach by a machine that was already on its way somewhere else. The spacecraft was Voyager 2, and it passed about 81,500 kilometers above the cloud tops of the planet. That sounds close, and by the standards of interplanetary travel it is. But the trajectory it flew was not chosen to serve the moons. It was chosen to bend the spacecraft onward toward Neptune, which lay another 12 years ahead. Every element of the encounter geometry followed from that requirement. Where the craft passed, how fast it moved, which moon it approached and at what range, and how long each target stayed in view, were all decided by celestial mechanics rather than by curiosity. The useful imaging window for each moon was short. Miranda received the closest attention because the trajectory happened to bring the spacecraft within about 29,000 kilometers of it. The best frames of Miranda resolve features down to a few hundred meters, which is genuinely good. For the other 4 moons, resolution is measured in kilometers per pixel. That is enough to establish shape, to map brightness patterns, to count the largest craters, and to notice the biggest fractures. It is rarely enough to establish process. A feature 5 kilometers across appears as a handful of pixels, and a handful of pixels can be read several different ways. Large regions of those moons are known only as smudges of light and shadow, and entire hemispheres are not known at all. That last point matters more than any other, and it follows directly from the tilt. The encounter took place during southern summer in the Uranian system. The sun was shining almost straight down onto the southern poles of the planet and of all 5 major moons. The northern hemispheres were not merely badly lit, or lit at an unhelpful angle, or partially obscured. They were in the middle of a polar night measured in decades. No sunlight was reaching them at all. A camera cannot photograph a surface that has no light falling on it. So roughly half of every one of these worlds has never been imaged by anything, ever. Half of Miranda. Half of Ariel. Half of Umbriel. Half of Titania. Half of Oberon. Not badly imaged. Not imaged at low resolution and then set aside. Not imaged. It is worth sitting with the size of that gap, because it is easy to skate past. Global maps of these moons exist, and at a glance, they look complete. They have named features, coordinate grids, color, and shading. But the northern halves of those maps are blank, or they are interpolated, filled in with what the terrain is assumed to do based on what the southern half is doing. Some published maps mark the region explicitly as unobserved, which is an unusual thing to find on a modern atlas of a solar system body. Every conclusion we hold about the geological history of these worlds rests on that one hemisphere each. How much resurfacing occurred? Whether the fractures are local features or global systems. Whether the strange terrains are anomalies or the normal condition of the surface. Whether the craters are evenly distributed or concentrated. All of it comes from half a world, photographed once at coarse resolution, under lighting that in places was so oblique that shadows exaggerated relief beyond its true scale, and in other places was so direct that relief vanished altogether. Consider what that does to the most basic tool in planetary geology, which is counting craters. The number of craters on a surface, sorted by size, is how ages are estimated. A heavily cratered surface is old. A lightly cratered one has been resurfaced. But the method assumes you have measured a representative area, and here the measured area is one hemisphere, illuminated from one direction, at a resolution that hides everything below a certain size. Small craters vanish into the noise. Craters near the terminator are exaggerated by long shadows. Craters near the subsolar point flatten out and disappear. The ages that come out of that process carry error bars measured in hundreds of millions of years, and they are quoted honestly, but the underlying data are far thinner than the confident numbers suggest. The same limitation applies to the fractures. A crack that runs across the imaged hemisphere and then reaches the terminator does not necessarily stop there. It may continue for another 1,000 kilometers across terrain no one has seen. Whether a fracture system is regional or global changes what it means entirely, and for every one of these moons, that distinction is unresolved. The same flyby also turned up 10 previously unknown moons and 2 additional rings in a matter of days. That is a useful measure of how much was hiding in plain sight before anything went there. An entire population of satellites orbiting a major planet, unsuspected until a camera passed by and caught them. There is a further complication, and it concerns the invisible part of the environment rather than the visible one. The spacecraft carried a magnetometer, and the measurements it made of the planet's magnetic field and the plasma around it have underpinned 4 decades of thinking about how the moons are being weathered. Later reanalysis of that record suggests the spacecraft may have arrived during an unusually compressed state of the magnetosphere, squeezed by a gust of solar wind, in a configuration that may hold only a small percentage of the time. If that reading is right, then the single direct sample we have of the environment these moons live in was taken on a day that was not typical. There are practical reasons the record is as thin as it is, and they are worth naming, because they are not failures of ambition. The imaging system aboard the spacecraft was designed in an era before digital sensors had matured. At the light levels found at Uranus, long exposures were necessary, and long exposures on a fast-moving spacecraft smear. The craft had to be slewed slowly during exposures to compensate, a maneuver that had to be planned in advance and could not be corrected in the moment. Data came home at low bit rates across an enormous distance. Some frames were compressed. Some were lost. And nothing about the encounter could be flown in real time. Light takes roughly 2.5 to 3 hours to travel one way between Earth and Uranus. A command sent from the ground arrives hours after it is issued, and the confirmation that it worked arrives hours after that. By the time anyone on Earth knew what the spacecraft was seeing, the spacecraft had already finished seeing it and moved on. In the years since, ground-based telescopes and space telescopes have added a great deal. Spectra have been taken. Temperatures have been measured. Compositions have been constrained. New small moons have been found, including one only about 10 kilometers across that the flyby missed entirely. Modern reprocessing of the original frames continues to pull detail out of images that were considered exhausted decades ago, and several recent findings about these moons have come not from new observations at all, but from old data examined with better tools. But no instrument has ever again resolved their surfaces at anything close to the resolution of that single pass. And because the flyby sampled exactly one season, the seasonal behavior of these surfaces has never been observed directly. It has only been modeled. That is the evidentiary position. 5 worlds, each of them larger than many of the bodies we consider well studied, and between them, a single afternoon of serious attention. One visit. Half of each one seen. A few hours of close looking, 4 decades ago, by a machine that could not slow down and could not come back. Everything that follows in this account is built on that foundation, and it is worth holding the thinness of it in mind as the details accumulate. Because what that thin record contains turns out to be considerably stranger than anyone expected. Part 3. Miranda and the Cliff. Miranda is the smallest of the 5 major moons and the most difficult object of its size anywhere in the solar system to account for. It is about 470 kilometers across, which places it near the lower limit for a body being round at all. Below roughly 400 kilometers, icy objects tend to keep whatever irregular shape they were assembled with. Miranda sits just above that line, barely spherical and slightly out of round. Objects that size are usually simple. A cold ball of ice and rock, saturated with craters, geologically finished within a few 100 million years of its formation and unchanged ever since. That is what small moons do. They lack the mass to retain internal heat, they lack the gravity to drive convection in their interiors, and they lack any mechanism to renew their surfaces once the early bombardment ends. Miranda is not that. Its surface is a collision of terrains that do not belong together. Ancient cratered plains run for hundreds of kilometers and then stop abruptly against enormous banded structures with sharp geometric outlines. The whole visible hemisphere is cut through by fault scarps at a scale that has no equal anywhere in the solar system, on any body, of any size. The most extreme of those scarps is called Verona Rupes, and it is the reason this small moon has a reputation far larger than itself. It is a cliff. In technical terms, it is a fault escarpment, formed where one block of crust dropped relative to the block beside it, leaving a wall of exposed material along the boundary. Estimates of its height run from about 5 kilometers at the conservative end to something approaching 20 kilometers at the high end. Even the conservative figure would make it a serious rival to anything on Earth. The upper figure makes it the tallest known cliff in the solar system by a very wide margin. 20 kilometers is difficult to hold in the mind, so it helps to place it against familiar things. The Grand Canyon is about 1.5 miles deep at its deepest. Verona Rupes, at the high estimate, would be roughly 10 times that. Everest rises about 8.8 kilometers above sea level. This is more than twice that height, in a single drop, on a world you could walk across in a few weeks. The uncertainty in those figures is not carelessness, and it is worth understanding where it comes from. The height was not measured directly. It was inferred from the lengths of shadows and from the profile of the terrain against the edge of the disk, in a small number of frames, taken at one particular sun angle on one hemisphere during a single pass. Shadow length depends on the angle of the light, on the slope of the ground the shadow falls across, and on the exact geometry of the camera. Small errors in any of those propagate into large errors in the answer. So the honest statement is that the tallest cliff we know of is somewhere between 5 and 20 kilometers high, and that the range has not narrowed in 4 decades because no one has been back to narrow it. The uncertainty is itself part of the story. But even the low end of the range demands an explanation, because a wall of that height should not be able to stand. On Earth, a cliff 20 kilometers tall would not survive its own construction. Rock has finite strength, and under Earth's gravity, a column of material that tall generates enough pressure at its base to crush and flow. Mountains on Earth are limited by this. Everest is close to the practical ceiling for a peak on a world of this mass. Anything substantially taller would sink into the crust supporting it. Miranda escapes that limit through 2 circumstances. The first is gravity. Surface gravity on Miranda is about 8/1000 of Earth's, which means the weight pressing down on the base of that cliff is almost 120 times less than the equivalent weight would be here. The second is temperature. Water ice at 60 to 85 Kelvin does not behave like the ice in a glass of water. It behaves like rock. It is brittle, strong, and capable of holding a shape indefinitely because there is not enough thermal energy anywhere in the system to let it creep or flow. Put those together, and a structure that would be physically impossible on a warmer, heavier world becomes not just possible, but stable. The cliff has probably been standing, essentially unchanged, for a very long time. The consequence of that same weak gravity is the detail that has made Verona Rupes famous, and it is worth working through slowly because it inverts the expectation. If you stepped off the top edge, you would not plunge. You would drift. Acceleration under Miranda's gravity is so gentle that for the first several seconds you would barely register that you were falling at all. The cliff face would begin to slide upward past you, slowly at first, then steadily faster. And it would keep sliding for a long time. The fall from the top of Verona Rupes to its base would take something on the order of 12 minutes. 12 minutes is an extraordinary length of time to be falling. It is long enough to watch the terrain below resolve from a pattern into a landscape. Long enough to turn and look at the wall you left. Long enough to think about it carefully, and then to keep thinking about it, and then to keep thinking about it some more. And it would still be fatal. That is the part people usually get wrong. Gentle acceleration applied for 12 continuous minutes accumulates. By the time you reach the base, you would be traveling at roughly 200 kilometers per hour. There is no terminal velocity to save you, because there is no atmosphere to provide drag. Nothing slows the fall. It simply continues, quietly, for 12 minutes, and then it stops all at once. That is a fair description of the entire system, in miniature. Nothing there is violent in the moment. Everything is slow. And the slowness is not a mercy. There are other things about Miranda worth noting before moving on. Its mean density, near 1 2/10 grams per cubic centimeter, is the lowest of the 5, implying a composition weighted heavily toward ice over rock. Its orbital period is about 1.5 days, and it is tidally locked, so the planet hangs motionless in its sky. Its orbit carries a small but unmistakable inclination, unusual for a regular satellite, and generally read as a fossil left behind by some past orbital arrangement that no longer exists. Some of the fault scarps show terracing, which suggests the crustal blocks dropped in stages rather than in a single motion. Bright material exposed along the scarp faces is probably cleaner ice, excavated from beneath a darkened surface layer, which means the walls themselves are windows into what lies just below. And because gravity is so weak, ejecta thrown up by an impact anywhere on Miranda can travel most of the way around the Moon before landing, or leave it altogether. Escape velocity there is only about 190 meters per second. Material knocked loose does not settle politely near the crater that produced it. It scatters across the entire world, and some of it never comes back down. That last effect has a consequence that is easy to overlook. On a world where impact debris is routinely thrown clear of the surface entirely, the material that does come back down has been mixed across the whole globe. There is no local geology in the way there is on a large planet. A sample taken anywhere on Miranda would contain fragments of everywhere else on Miranda, redistributed slowly over billions of years by a long sequence of small collisions. The surface is, in a sense, continuously stirred, though the stirring happens once every few million years rather than continuously in any human sense. Grooved terrains appear on Miranda as well, in places resembling features found on much larger icy moons, though here they run at a fraction of the scale. And that resemblance is the first hint of the difficulty. The processes that carve grooves into a large moon require sustained internal warmth. Miranda should never have had any. All of which is context for the feature that actually makes Miranda strange, and which we have not yet reached. Part 4. The Racetracks. The features that dominate Miranda's imaged hemisphere are not craters, and they are not mountains. They are 3 enormous structures called coronae, and the only reason that word exists in this context is that nothing else in the solar system looks like them. Each corona is a broadly ovoid to trapezoidal province, hundreds of kilometers across, filled with concentric bands of ridges and troughs that follow the outline of the province the way contour lines follow the shape of a hill. They have been described as racetracks, as plowed fields, and as chevrons. All 3 descriptions are fair, and none of them is quite adequate. The largest is Arden, which sits on the leading hemisphere, the side that faces forward along Miranda's orbital path. It is roughly 300 kilometers across, with broad banded terrain and an outer boundary that cuts sharply into older ground. Elsinore lies on the trailing side, comparable in scale, older in appearance, its banding softened by later impacts. And the third is Inverness, the sharply angular one, smaller than the others but far more striking, with a bright pale chevron near its center that forms a rough letter V across the terrain. It is the feature most people recognize even if they have never heard this moon's name, and it is the reason Miranda appears in photographs of the outer solar system far more often than a body its size otherwise would. What makes the coronae genuinely difficult is not their appearance. It is their edges. They do not fade into the surrounding terrain. They stop. Ancient, heavily cratered plains, the sort of surface that has been sitting undisturbed since the early history of the solar system, run right up to a boundary. And then, across a distance of only a few kilometers, the ground becomes something else entirely, younger, banded, structurally organized, with far fewer craters and a completely different texture. The transition is abrupt enough to look artificial in the images, which is part of why the Moon has attracted the attention it has. On a body this small, that is very hard to explain. Small worlds shed their internal heat quickly, because the amount of heat a body holds scales with its volume, while the rate at which it loses that heat scales with its surface area. Shrink a world and the ratio turns against it sharply. Miranda should have frozen through early and stayed frozen. There should not have been an engine available to build structures of this kind, and there should certainly not have been one available to build them more than once. The older explanation, which is still the version most people have heard, was catastrophic. In that account, Miranda was shattered by an impact severe enough to break it apart, and then reassembled under its own weak gravity from the resulting fragments. The coronae, in this reading, were pieces of the interior that never fully settled back into place, left protruding through a surface stitched together from mismatched parts. It is a vivid idea. It matches the visual impression of the Moon perfectly, and it is memorable enough that it has outlived its own scientific standing by decades. It has largely fallen out of favor. The trouble is that a reassembled rubble pile would not produce what the coronae actually show. Concentric, ordered, tectonically coherent banding requires the crust to have been deformed in a systematic way by a sustained force. A pile of fragments settling together produces chaos, not contour lines. And the reassembly account cannot easily explain the clean separation in age between one province and another, or why the terrain inside a corona is consistently younger than the terrain outside it. The explanation that has taken its place is slower, and in its way more unsettling. It holds that the coronae are surface expressions of upwelling from within. Warm, buoyant material rising in broad columns from the interior, pressing against the underside of the crust, deforming it and stretching it as the material spreads outward beneath it. The concentric ridges and troughs are the record of that stretching, laid down in bands as the surface was pulled apart above a rising plume. Some models achieve a similar result in reverse, with dense material sinking rather than warm material rising, and the surface collapsing inward above it. The details differ. The requirement does not. Either version requires sustained internal heat, and the only plausible source of sustained heat in a body of Miranda's size is tidal flexing, driven by orbital resonance with the neighboring moons. The mechanism is straightforward. When two moons settle into orbital periods that form a simple ratio, one completing exactly 2 orbits for every one of its neighbors, or 3 for every 2, their gravitational tugs stop averaging out and start reinforcing each other. The repeated pulls stretch the orbit into a slightly more elliptical shape. And an elliptical orbit means the Moon's distance from the planet changes over the course of each circuit, which means the tidal bulge raised on it by the planet rises and falls with every orbit. That flexing generates friction. The friction generates heat. And on a body kneaded that way for long enough, the heat can be enough to melt ice. There is a loose analog elsewhere, though it works in an entirely different material. Venus carries large circular structures, also called coronae, formed where plumes of hot rock rise beneath a silicate crust and push it upward before it sags back. They are far larger than Miranda's, and they are made of stone rather than ice. But the underlying idea is the same, a surface deformed from below by something rising. Finding that process operating on a world of 470 kilometers in water ice at temperatures near 80 Kelvin is the part that resists easy acceptance. There is also a reason the provinces sit where they sit rather than being scattered at random. Tidal heating is not distributed evenly through a flexing moon. The stresses concentrate in particular latitudes and particular depths depending on the geometry of the orbit and the structure of the interior. A moon being kneaded by its neighbors warms unevenly, and the warm regions are where upwelling would be expected to occur. The positions of Arden, Elsinore, and Inverness may therefore be a map of where Miranda was warmest, preserved in the crust long after the warmth itself was gone. Crater counting supports a long, staggered history rather than a single event. Elsinore appears to be the oldest of the three provinces, at something on the order of 1 billion years, though the uncertainty on that figure spans most of 1 billion years in either direction. Inverness appears to be the youngest, possibly as recent as 100 million years, again with generous error bars. Arden sits somewhere between them. If those numbers hold even approximately, then Miranda was not resurfaced once, long ago, and then left alone. It was resurfaced repeatedly, in separate episodes, spread across a substantial fraction of the age of the solar system. And the most recent of those episodes was, in geological terms, close to the present day. There are supporting details that point the same way. The fault patterns inside the coronae indicate extension rather than compression. The crust was pulled apart, not squeezed together, which is what you would expect above rising or spreading material. The spacing between ridges carries information about how thick and how strong the crust was when they formed, and that spacing varies between provinces, suggesting conditions changed between episodes. Arden's outer bands are cut by later faults, showing the province continued to deform after it had formed. And the bright chevron at the heart of Inverness is bright because the material exposed there is cleaner ice than the darkened surface around it, which means it has been exposed comparatively recently. The chevron itself deserves a moment, because it is the single most recognizable thing about this moon. It is a pale, angular band, cutting across the darker banded terrain of Inverness at a sharp angle, forming a shape the eye reads immediately as deliberate. It is not deliberate. It is a set of fault-bounded blocks where cleaner ice has been exposed along the scarps, and the geometry that makes it look drawn is simply the geometry of the faults that produced it. But it photographs so well, at such low resolution, that it has become the visual shorthand for the entire Uranian system. There is one caveat that hangs over all of it, and by now it will be familiar. Everything just described comes from one hemisphere. There could be additional coronae on the unseen side of Miranda. There could be none. There could be terrain types that do not appear anywhere in the observed half at all. Whether these three provinces are the exception on this moon or the rule is not a question anyone can currently answer, and the difference between those two possibilities changes the interpretation completely. Part 5. The ocean that should not have fit. The question that follows naturally from the coronae is what was underneath them, and the answer that recent modeling has produced is difficult to accept on first hearing. The method is indirect but sound. A surface records the forces that shaped it. The pattern of the faults, the depth and spacing of the ridges, the total amount of stretching the crust must have undergone, the way the deformation is distributed across a province. All of these depend on what the crust was resting on when it deformed. Work backwards from the surface with enough care, and you can constrain the interior that produced it. Some interiors are consistent with the observations. Most are not. When that exercise was carried out for Miranda, the interior that fit best was not a solid ball of ice. It was an ocean. The numbers are the striking part, and they need to be stated slowly. The modeled ocean is at least 100 kilometers deep. It sits beneath an ice shell no more than about 30 kilometers thick, and Miranda's radius is only about 235 kilometers. Work that through. An ocean 100 kilometers deep inside a body with a radius of 235 kilometers does not sit in a basin at the bottom of the world. It is not a sea. It occupies something close to half the entire volume of the Moon. For a period of its history, Miranda may have been less an icy world with some water inside it, and more a globe of water with a thin rind of ice on the outside, held together by its own faint gravity, turning slowly in the dark. The timing is equally awkward. The modeling does not place this ocean in the deep past, in the first violent 100 million years, when everything in the solar system was warm and unfinished. It places it within roughly the last 100 to 500 million years. That is recent enough to overlap with the youngest corona ages. It is recent enough that a remnant of that ocean could plausibly still exist today, much colder, much saltier, much thinner, pressed into a layer rather than filling a hemisphere, but not gone. The heat to sustain it would have come from orbital resonance. At some point in the past, Miranda's orbital period sat in a simple ratio with the neighboring moons. The repeated gravitational tugs stretched its orbit, and the stretched orbit meant the tidal bulge raised by the planet rose and fell with every circuit. That flexing warmed the interior from within, exactly as friction warms anything that is bent back and forth for long enough. Resonances, however, are temporary. Moons migrate slowly outward or inward, and eventually the ratio breaks. When it does, the flexing stops, the heating stops, and the ocean begins to freeze from the outside in. The lingering inclination in Miranda's orbit today is generally read as a fossil of exactly that, the signature of a resonance the Moon passed through and then escaped, leaving the tilt behind as a receipt. And a freezing ocean is not a quiet thing. Water expands as it turns to ice. A thickening shell above a shrinking ocean puts the crust under stress, and that stress has to go somewhere. Some of the deformation visible on Miranda's surface may be the record not of the ocean's existence, but of its ending. What makes this genuinely unsettling, rather than merely surprising, is that it contradicts the other well-supported picture of the same moon. Independent modeling of the entire family of 5, built on reanalyzed flyby data and modern understanding of how icy bodies retain heat, concludes that Miranda is simply too small. The argument is the straightforward one. Heat scales with volume, loss scales with surface area, and at 470 kilometers across the arithmetic is decisively against you. In that analysis, the smallest of the 5 should have frozen through early and remained frozen ever since, and the 4 larger moons are the ones with any prospect of holding liquid water today. Both analyses are careful. Both are built on real data. Both are published in good faith by people who understand the limitations of what they are working with. And they point in opposite directions about the same moon. The observation that would settle it is not exotic. A salty ocean inside a moon is electrically conductive, and a conductive layer responds to a changing external magnetic field by generating a field of its own. That induced field can be measured by a spacecraft passing close by, and its strength and timing reveal not just whether an ocean is present, but roughly how deep and how salty it is. Alternatively, precise tracking of a spacecraft during repeated close passes can detect the way a shell floating on liquid flexes differently from a solid body, which is an independent test of the same question. Uranus happens to be unusually well suited to the first method, for reasons that have nothing to do with convenience and everything to do with the planet's oddity. Its magnetic field is tilted far from its rotation axis and offset from the planet's center, so it does not sweep past the moons as a steady, uniform presence. It sweeps past them as a strongly varying signal, several times a day. For a technique that depends on a changing field that is close to ideal conditions. There is a third approach as well, and it is the one that transformed our understanding of Enceladus. If material from an interior ocean reaches the surface and escapes, a spacecraft can fly through it and measure it directly. No plume has ever been detected at any Uranian moon. But no plume has ever been searched for at close range either, and a search conducted from nearly 3 billion kilometers away through a telescope would struggle to detect anything short of a spectacular one. The measurement has never been made. Not because it is difficult in principle, and not because anyone doubts it would work, but because making it requires a spacecraft in orbit around Uranus, making repeated close passes of each moon, and no such spacecraft has ever existed. So the position we are actually in is this. The smallest major moon of Uranus either holds the remains of an ocean that once filled half its volume, or it cannot possibly hold one and never could. The evidence for both readings comes from the same thin set of images. And the instrument that would decide between them has not been built, launched, or funded. A few supporting details are worth carrying forward because they will matter later. Ammonia dissolved in water can depress its freezing point by tens of Kelvin, which at these temperatures is an enormous effect, the difference between an ocean and a solid. Chloride salts do something similar, and they also make the water conductive, which is precisely what allows the magnetic test to work. And tidal heating rates depend very steeply on orbital eccentricity, so a small change in a moon's orbit produces a disproportionately large change in how warm its interior becomes. The question of where the water went, if it was ever there, is worth holding as well. An ocean that freezes does not vanish. It becomes part of the shell above it, thickening that shell from below over tens of millions of years. If Miranda's ocean froze, the ice that formed from it is still there, and the moon we see is largely made of it. And a shell thickening from below tends to leave compressional features on the surface as the crust is forced to accommodate the expansion. Whether such features exist on Miranda is not known, because the hemisphere most likely to record them has never been photographed. That is not a rhetorical flourish. It is a genuine, testable prediction that has been sitting unresolved for 4 decades for want of a camera pointed in the right direction at the right time of year. There is also a nearby precedent that keeps the possibility open. Enceladus, orbiting Saturn, is comparable in size to Miranda and is unambiguously active, venting water into space through fractures at its south pole, driven by exactly this kind of resonant flexing. The existence of Enceladus establishes that small bodies can sustain oceans under the right orbital conditions. It does not prove that Miranda did, but it removes the easy objection that a world this size simply cannot. Part 6. Ariel, the Bright One. Moving one step outward from Miranda brings us to Ariel, and to a world that looks nothing like its inner neighbor, and nothing like the moon immediately beyond it either. Ariel is about 1,158 kilometers across, which makes it comfortably the 4th largest of the 5. It is also the brightest surface in the system, reflecting roughly 1/3 of the light that falls on it. That may not sound remarkable, but in this family it is a considerable outlier. Its nearest neighbor outward, Umbriel, reflects only about half as much. In an environment like this one, brightness is a symptom rather than a property. Surfaces in the outer solar system darken steadily over time. Charged particles bombard them, splitting apart the molecules in the ice and leaving darker residues behind. Micrometeorites churn the top layer. Carbon-bearing compounds slowly convert into reddish and black material that absorbs light rather than returning it. Given 4.5 billion years, any exposed icy surface out there should be dark. So a bright surface means fresh material. And fresh material means the moon has been renewing itself. The imaged hemisphere supports that reading in several independent ways. Ariel has the fewest large craters of the 5, which is the standard indicator that a surface is comparatively young. Craters accumulate over time, and the only way to reduce the count is to cover them, fill them, or erase them. Somewhere in Ariel's history, something did. Then there are the valleys. Ariel is cut through by an extensive network of chasmata, long, steep-sided rift valleys that run for hundreds of kilometers and reach several kilometers deep. Rift valleys form where a crust is pulled apart and a block of it drops between two faults. That much is ordinary, and similar structures appear across the outer solar system. What is not ordinary is what is inside them. Many of Ariel's chasma floors are flat, smooth, and marked by a groove running down the middle, and they sit well above where the bottom of the fracture ought to be. A rift valley that has simply opened and stayed open has a rough, blocky floor made of collapsed wall material. These do not. They look filled. The natural reading, and the one that has held up, is that something flowed into these valleys from below, pooled there, and froze. At Ariel's temperatures, that flow was not molten rock. It would have been a cold slurry of water ice mixed with ammonia or with dissolved salts, both of which lower the melting point substantially, and both of which produce a thick, viscous material that behaves in flow much the way lava does on Earth. It would have moved slowly, spread across the valley floor, and set hard. The medial grooves running down the centers of some of those floors resemble features on other icy moons, where they mark the last stage of refreezing, as the surface contracted over a still liquid interior. This is cryovolcanism in the plain sense of the word. Not eruption in the dramatic sense, but a cold, slow welling up of material from inside a world onto its surface. And it requires an inside that had something to give. The chemistry has recently added a harder edge to all of this, and the story it tells is more direct than the geology. Ariel carries some of the most concentrated deposits of carbon dioxide ice known anywhere in the solar system. That alone is notable. What makes it interesting is that the deposits are not distributed evenly across the moon. They are strongly concentrated on the trailing hemisphere, the side that faces backwards along the direction of Ariel's orbit. There are two ways to produce a pattern like that, and they have quite different implications. The first is external. The planet's magnetosphere rotates with the planet in about 17 hours, while Ariel takes about 2.5 days to complete an orbit. The magnetosphere therefore overtakes the moon continuously, and the charged particles it carries sweep preferentially onto the trailing hemisphere. Those particles carry enough energy to break chemical bonds in surface ice. Given water ice and any carbon-bearing material mixed into it, they can manufacture carbon dioxide directly, in place, over long periods. The pattern would then be a record of bombardment rather than of anything internal. The second is internal. In this account, the carbon dioxide is leaking out from inside the moon, escaping through fractures in the crust, and freezing onto the surface where it emerges. And there is a suggestive detail here. Most of Ariel's grooves, the features that would serve as pathways from the interior to the surface, are also on the trailing side. The two explanations predict the same geography for different reasons, which is exactly the situation that makes a question difficult. Two more recent findings tilt the balance toward the interior. The first is carbon monoxide. Infrared observations have detected carbon monoxide ice on Ariel's surface, and carbon monoxide has no business being there. At the temperatures found on that surface, it sublimates away far too quickly to be a leftover from the moon's formation. Anything we see now must have arrived recently, or must be arriving continuously. Something is replenishing it. Radiolysis could do that, but so could an interior that is still outgassing. The second finding is subtler and, in the long run, probably more important. The same spectra carry hints of carbonate minerals. Carbonates form where liquid water interacts chemically with rock. They are not a product of radiation striking ice. They require water and rock in contact, with time to react. Finding traces of them on the frozen surface of a small icy moon implies that somewhere below, water and rock met, and that some of the product of that meeting found its way up to where a telescope could see it. That is a very quiet piece of evidence, delivered from a distance of nearly 3 billion kilometers, and it is currently among the strongest indications we have that any of these worlds holds liquid water. The question of where Ariel's warmth came from has a plausible answer, and it is the same mechanism that appears everywhere in this system. Ariel and Umbriel may once have occupied an orbital resonance with one another, their periods locked in a simple ratio for some extended stretch of the past. While that arrangement held, both orbits would have been stretched into slightly more elliptical shapes, and both moons would have been flexed by the planet on every circuit. Ariel, being closer in, would have been flexed harder. The energy involved is not small when it is applied for hundreds of millions of years, and it is currently the leading candidate for the heat that drove the resurfacing we can see. If that is what happened, then Ariel's bright surface is a record of a relationship rather than a property of the moon itself. Two worlds happened to fall into step with one another, and one of them melted as a result. When the resonance broke, the heating stopped, and everything since has been the slow business of cooling down and darkening again. There is a practical difficulty in resolving any of this from where we sit. The trailing hemisphere is both the side most exposed to the plasma and the side where the fractures are concentrated. The two candidate explanations for the carbon dioxide, therefore, make overlapping predictions about where the deposits should be, and a spectrum taken from a great distance cannot easily separate them. Distinguishing gas made by radiation from gas exhaled by an interior may require measuring the material directly, in place, with an instrument close enough to sample what is actually there. Ariel's other properties are worth noting in passing. Its surface gravity is roughly 27 thousandths of Earth's, low enough that a person could jump several meters without effort and come down slowly. Its orbital period is about 2.5 days, and like the others, it is tidally locked. Its density, near 1 6/10 grams per cubic centimeter, is essentially the same as Umbriel's. That last point is the one that lingers. Ariel and Umbriel are nearly identical in size and nearly identical in composition. They orbit the same planet, in the same plane, a few 100,000 kilometers apart. One of them has been resurfaced, flooded from below, and appears to be exhaling gas into space. The other, as we are about to see, looks as though nothing has happened to it in 4 billion years. Part 7. Umbriel, the Dark One. It is worth pausing here to restack what has accumulated so far, before going further out. 5 worlds, tipped on their sides with the planet they belong to, each locked into a rhythm of 42 years of dim light and 42 years of unbroken night. One spacecraft, one pass, 4 decades ago, with the northern half of every moon in darkness, and therefore unphotographed. A moon the size of a small country, carrying the tallest cliff known anywhere, a wall of ice that would take 12 minutes to fall down. 3 provinces of banded terrain on that same moon that nothing else in the solar system resembles, and modeling which says it once held an ocean filling half its volume, set against other modeling which says that is impossible. And beyond it, a neighbor whose valleys appear to have been flooded from below and whose surface is exhaling a gas that should have vanished long ago. That is where we are. And we have not yet reached the moon that is genuinely difficult to explain. Umbriel is almost exactly the same size as Ariel. About 1,169 kilometers across, against Ariel's 1,158. The difference between them is a matter of a few kilometers in diameter, well within the uncertainty of some early measurements. Their densities are close enough to be treated as identical. They formed in the same disk, from the same material, around the same planet, in the same era. And Umbriel is the darkest of the five, reflecting only around 16% of the light that reaches it. It is also the second most heavily cratered after Oberon, with a surface that appears essentially unmodified since early in the system's history. Craters upon craters, saturated, ancient, and undisturbed. Two neighboring moons, effectively identical in size and composition, orbiting a few 100,000 kilometers apart. One of them resurfaced, bright, fractured, and apparently still leaking. The other dark, static, and to all appearances dead. Nothing in the standard picture accounts for that cleanly. It is one of the sharpest unresolved contrasts in planetary science, and it sits in a system almost nobody thinks about. The darkness itself is not fully understood, which is its own small oddity. Something has coated or altered Umbriel's surface uniformly across the entire imaged hemisphere with remarkable consistency. There are three main candidates. The first is charged particle processing. Umbriel orbits within the planet's magnetosphere, and over billions of years, the constant bombardment breaks down molecules in the surface ice and leaves behind darker, carbon-rich residues. This process operates everywhere in the outer solar system and reliably darkens exposed surfaces over time. The second is infall. The distant irregular moons, far out on their tilted and often backward orbits, are being slowly ground down by collisions, and the dust they shed spirals inward. Some of it lands on the major moons. If that dust is dark, and it probably is, then Umbriel has been receiving a slow dusting of it for a very long time. The third is internal composition. If Umbriel's ice carried more carbon-bearing material to begin with than Ariel's did, it would darken faster and more thoroughly under the same conditions. None of these explanations accounts for why Umbriel should be so much darker than a neighbor of identical size sitting right beside it, unless the answer is simply that Ariel keeps renewing its surface and Umbriel does not. Which returns us to the same question in a different form. Against that uniform darkness sits the one feature Umbriel is known for. Near its equator lies a crater called Wunda, about 131 kilometers across. And on the floor of that crater is a ring of bright material, roughly 80 kilometers in diameter, at least 10 kilometers wide, forming a clean circle on an otherwise unremarkable crater floor. Consider the situation carefully. On a moon where nothing is bright, there is exactly one bright thing. It lies on the floor of a crater. It sits close to the equator, and it is a ring rather than a patch, a smear or a central peak. The most likely explanation is that Wunda's floor acts as a cold trap. Volatile compounds, particularly carbon dioxide, are mobile on these surfaces. Sunlight liberates them from warmer terrain, they drift as gas, and they refreeze wherever they encounter somewhere cold enough to hold them permanently. A crater floor, shadowed for much of the long seasonal cycle, is exactly such a place. Under this reading, the bright ring is not a structure at all. It is a deposit. Frost, accumulated over a very long time in the one place on that hemisphere where it can stay. Another line of work asks a different question, whether the impact that formed Wunda punched deep enough to trigger cryovolcanic activity beneath it, allowing material from below to well up and fill the crater floor. In that reading, the ring is not frost that arrived from elsewhere. It is cleaner material that came up from inside. Both explanations require Umbriel to be less inert than it looks. The cold trap version requires an active volatile cycle moving material across a supposedly dead surface. The cryovolcanic version requires an interior with something to contribute. Neither is consistent with the picture of a moon that froze solid 4 billion years ago and has been sitting still ever since. And there is a final frustration attached to this feature, which by now will be entirely predictable. Wunda sits close to the Terminator in the only images that exist of it. The lighting there is extremely oblique, the resolution is poor, and the feature is small in the frame. The brightest object on the darkest moon in the Uranian system has been seen once, at a bad angle, in low resolution, and then never again. It is worth dwelling on how cold trapping actually works, because it is one of the quiet engines running throughout this system. A molecule of carbon dioxide sitting on a sunlit surface at 80 Kelvin has a small but real chance of gaining enough energy to lift off. Once free, it follows a ballistic arc across the moon, because there is no atmosphere to slow it, and gravity is weak. It lands somewhere else. If that somewhere else is warm enough, the process repeats. If it is cold enough, the molecule stays. Run that for 1 billion years, and the volatiles migrate steadily from every warm place to every cold place, until the cold places are full and the warm places are stripped bare. Crater floors near the equator can serve as cold places because their walls shade them for much of the long seasonal cycle. Polar craters do it better still, because at high latitude, the sun never rises far above the horizon, even at the height of a 21-year summer, and some floors never receive direct light at all. Those are permanent traps. Whatever falls into them stays for the lifetime of the moon. This means the bright ring on Wunda's floor may be a record of what the rest of Umbriel used to have. A dark, stripped surface, and one bright circle where everything the surface lost has been collecting, patiently, since long before there was anyone to notice. There is also a small self-reinforcing effect worth naming. A dark surface absorbs more of the sunlight that reaches it than a bright one does, which warms it very slightly. That extra warmth makes volatiles marginally more mobile, which strips the surface further, which makes it darker still. The effect is tiny in any given year. Over 4 billion years, tiny effects finish their work. A few other details are worth carrying forward. Umbriel's orbital period is about 4 days, and it is tidally locked like the rest. Some of its craters show faint, bright central peaks, which suggests cleaner ice lies just beneath the dark surface layer rather than throughout the body, meaning the darkening is a coating rather than a fundamental property. And notably, the same modeling that questions whether Miranda could hold an ocean places Umbriel firmly among the moons that could, despite its dead-looking surface. That is the difficulty with judging these worlds by appearance. A dark, cratered, undisturbed surface tells you what has happened at the top over billions of years. It tells you almost nothing at all about what may be happening 100 kilometers further down. Part 8. Titania and Oberon, the big quiet ones. The two outermost of the 5 are also the largest, and they are the least discussed. That is not because they are uninteresting. It is because they were imaged from the greatest distance and yielded the least detail, and there has been correspondingly less to say. Titania is about 1,578 kilometers across, which makes it the 8th largest moon in the solar system. Oberon, at about 1,523 kilometers, is close behind. Both are roughly half water ice and half rock by mass. Both are tidally locked, keeping one face permanently toward the planet. Both, at the resolution available, look like ordinary cratered ice worlds. The details that survive the poor resolution are the interesting part, and there are not many of them. Titania is cut by a fracture system called Messina Chasmata, and it is enormous. A set of roughly parallel troughs running for something on the order of 1,500 kilometers across the imaged hemisphere, reaching several kilometers deep in places. On a body this size, that is a scar running most of the way around the world. Systems like it form when a crust is stretched. The question is, what did the stretching? And for an icy moon, there is a very tidy candidate. Water is unusual among common substances in that it expands when it freezes. A moon with an interior ocean that gradually solidifies, therefore swells slightly as the freezing proceeds. The increase in volume is small in percentage terms, but the outer shell is brittle and cannot stretch. It cracks instead, and it cracks in long parallel systems that run across the surface. Global fracture networks of this kind are one of the standard signatures of an ocean that used to be there and is not any longer. There is a second piece of information hidden in those troughs, and it is more subtle. Along parts of the chasmata, the rims are raised. When a crust is loaded or unloaded, it flexes, and the shape of that flexure depends on how thick and how warm the crust was at the time. Measure the profile of a raised rim carefully enough, and it becomes possible to estimate how much heat was flowing out of the moon when the feature formed. A set of trough profiles, in other words, functions as a rough thermometer reaching back 1 billion years or more. Titania shows fewer large craters than Oberon does, which implies that some resurfacing occurred after the era of heavy bombardment ended. There is also a very thin carbon dioxide signature associated with it, raising the possibility of an extremely tenuous seasonal atmosphere, one that would freeze out onto the winter hemisphere during the long night and return as gas when the sun came back. It would be nothing like an atmosphere in any familiar sense. It would be a trace of vapor, cycling on a 42-year rhythm. Oberon is the outermost of the 5 and the most heavily cratered. On the evidence available, it is also the least modified, a surface that appears to have recorded everything that struck it and changed in no other way. But 2 features stand out from that uniformity. The first is that several of its large craters have unusually dark floors. Not dark in the way the whole moon is dark, but distinctly darker than their surroundings, in a way that suggests material welled up and pooled inside them after the impacts, rather than being deposited from outside. If that reading is right, then Oberon, the most inert-looking of the 5, has had material moving up from its interior at some point in its history. The second feature is stranger, and it is the kind of observation that could only come from a flyby. Along the limb of the moon in one image, silhouetted against black sky at the very edge of the disk, there is a peak. Because it appears in profile rather than in shadow, its height can be estimated by simple geometry. You are not modeling a shadow length against an uncertain sun angle across unknown terrain. You are measuring how far the outline of the moon departs from a circle. The estimate that comes out is near 11 kilometers. That is taller than Everest. On a moon with roughly a 40th of Earth's surface gravity, seen once, edge-on, in a single frame, by a spacecraft that never came back and was never designed to look. Nobody knows what it is. It might be the central peak of an enormous impact basin, uplifted by the rebound of the crust after the impact. It might be the rim of such a basin, caught at the right angle. It might be something else entirely. Because it was seen only in profile, we know its height reasonably well, and essentially nothing else about it. There are no images of it from any other angle, because there are no images from any other angle of anything on that moon. It is worth noting how much rests on crater counting for these two moons in particular, and how shaky that foundation is out here. The method works by comparing the number and size distribution of craters on a surface to an assumed rate of impacts over time. On the moon, that rate is calibrated against rocks brought back and dated in laboratories. In the outer solar system, there is no such calibration. The population of objects doing the cratering is poorly known, its history is poorly known, and the rate at which it delivered impacts billions of years ago is estimated rather than measured. So when a surface is described as roughly 1 billion years old, the number is doing real work, but the uncertainty attached to it is enormous, and the ranking of one moon against another is far more reliable than any absolute age. The largest impact basins on Oberon are hundreds of kilometers across. An impact capable of excavating a structure that size delivers an extraordinary amount of energy into a small world, and a substantial fraction of it converts to heat. Locally, temporarily, the interior beneath such a basin would have warmed considerably. If any liquid existed below, or if any ice was close to melting, a strike of that magnitude could have mobilized it. That is one of the more plausible routes to the dark material pooled on those crater floors. Not a general volcanic phase across the whole moon, but individual impacts, each triggering a local response beneath themselves. There is also the question of what these two look like from the ground, which is worth registering before moving on. From Oberon's surface, the planet still spans about 5 degrees of sky, roughly 10 times the apparent width of the full moon as seen from Earth. It hangs in a fixed position, never rising, never setting, showing its pale blue-green face and faint banding. From Titania, it is larger again. And from the far hemisphere of either moon, it is not visible at all, and never has been. That is genuinely the state of knowledge for the two largest worlds in the Uranian system. One enormous fracture system on one hemisphere of one of them. One population of dark, flawed craters. One mountain seen once in profile against the edge of the disk. Everything else is inference, drawn from brightness measurements, spectra, density estimates, and models. There are no maps of their northern halves. There is no measurement of their interiors. There is no gravity field determination, no magnetic induction search, no thermal mapping, no close spectroscopy. The two biggest bodies orbiting the 7th planet are, in the most literal sense available, mostly unexamined. A few closing details on this pair. Titania's orbital period is about 8 3/4 days. Oberon's is about 13.5. Oberon orbits far enough out that it spends part of each circuit outside the planet's magnetosphere, which gives it a genuinely different surface processing history from the inner 4, and may partly explain differences in its color. Both moons show reddening on their leading hemispheres, most likely from sweeping up dust shed by the distant irregular moons as they orbit. And because Titania is the largest of the 5, it retains internal heat better than any of the others. In the modeling that has been done of this system, it is the moon judged most likely to hold a liquid ocean at the present day. The largest, the least examined, the one with a 1,500-kilometer crack across the only side we have seen, and the best candidate for water still being there. Part 9. The case for water. Taken individually, the hints on each of these moons are suggestive, but not decisive. A flooded valley floor here. A replenished gas there. A bright ring on a crater floor. A crack running 1,500 kilometers. Each one has an alternative explanation, and each alternative is reasonable. Taken together, they have moved the entire system into a category it did not occupy a generation ago. Comprehensive modeling of the interiors of all 5 major moons has now been carried out, built on reanalyzed flyby data, updated estimates of composition, and a considerably better modern understanding of how icy bodies hold and lose heat. The conclusion is that 4 of them likely hold, or once held, a layer of liquid water between a rocky interior and an icy shell. Ariel, Umbriel, Titania, and Oberon all come out on the ocean side of the line. Titania, being the largest and therefore the best at retaining heat, has the strongest prospect of holding one still. The mechanism involved is not exotic, and it is worth walking through because it explains why the old assumption was wrong. Rock contains radioactive elements, and those elements release heat steadily as they decay. In a body made half of rock, that heat is generated continuously in the interior and has to escape through whatever lies above it. The old reasoning assumed the escape was efficient. If the interior is dense, compacted rock, heat conducts through it readily and the moon cools on schedule. But interiors may not be compacted. If the rocky portion is porous, riddled with pore space and fractures, it insulates rather than conducts. Heat generated in the middle stays in the middle, and the cooling timescale stretches by hundreds of millions of years. That single change in assumption is enough to keep water liquid in bodies that were previously written off as frozen through. Add antifreeze, and the problem becomes easier again. Chlorides and ammonia dissolved in water can lower its freezing point by tens of Kelvin. At the temperatures involved here, that is not a marginal adjustment. It is the difference between an ocean and a solid ball of ice. And both compounds are expected to be abundant in bodies that formed where these did. What emerges from this is not the warm, bright water that the word ocean tends to summon. The modeled oceans are cold, dense, and heavily salted. They are probably only tens of kilometers deep, sandwiched between rock below and ice above, under crushing pressure, in complete darkness, and they have been that way for billions of years. But they are liquid, and liquid water in contact with rock is the condition that makes any environment worth a second look. The surface evidence lines up with this in an untidy but consistent way, and it is worth assembling it in one place. Ariel's chasma floors appear to have been flooded from below by material that behaved like cold lava, and its surface carries carbon oxides that should have dissipated long ago and therefore must be replenished, along with spectral hints of carbonate minerals that only form where water and rock have interacted. Umbriel's one bright feature sits on a crater floor and may be sourced from below rather than deposited from elsewhere. Titania's global fracture system is the precise signature that a freezing ocean leaves in an outer shell, and the flexure recorded in its trough rims implies heat was once flowing out of the moon at a substantial rate. Oberon's dark crater floors look like infill, welling up after impacts that reached deep enough to mobilize something. And Miranda's coronae, and the modeling that follows from them, sit at the extreme end of the whole argument, describing an ocean that would have occupied half the moon. Not one of those is proof. Every one of them can be argued the other way, and responsible people do argue them the other way. But all of them are the kind of thing you would expect to see if these interiors were, or recently had been, wet. That is a different situation from having no evidence, and it is why the question is now taken seriously rather than dismissed. What would settle it is straightforward in principle. A conductive, salty ocean inside a moon responds to a changing external magnetic field by generating an induced field of its own. That induced field can be measured by a spacecraft flying close by. Its strength depends on how conductive the ocean is, which depends on how salty it is. Its timing and shape depend on how deep the ocean lies beneath the surface and how thick it is. A good measurement, therefore, returns not just a yes or a no, but a rough description of the water itself. Uranus is unusually well suited to this technique, and for once its peculiarity is an advantage. Its magnetic field is tilted about 59 degrees away from its rotation axis, and it is offset from the planet's center by roughly a third of a planetary radius. It is not a tidy dipole with the moons circling politely inside it. It is lopsided, and because the planet turns in about 17 hours, the field sweeps past each moon as a strongly varying signal several times a day. For a method that depends on a changing field, those are close to ideal natural conditions. There are supporting techniques as well. Precise radio tracking of a spacecraft during repeated close passes reveals a moon's gravity field and a shell of ice floating on liquid flexes differently from a solid body, so the tidal response itself becomes a test. High-resolution spectroscopy at close range could identify surface salts that would only be there if ocean material had reached the surface. And a search for plumes, conducted from close in rather than from 3 billion kilometers away, would settle in an afternoon a question that has been open for decades. There is one more variable that ties all 5 moons together, and it deserves stating plainly. The lifetime of an ocean inside any of these worlds depends heavily on the eccentricity of its orbit, because eccentricity drives tidal heating. And eccentricity is not a fixed property. It rises and falls as moons pass into and out of resonance with one another over hundreds of millions of years. Which means each moon's water record is bound up with the orbital history of its neighbors. Ariel's warmth may have come from a period of lockstep with Umbriel. Miranda's may have come from a period of lockstep with something further out. None of these worlds warmed itself alone. That interdependence has a consequence worth carrying. If one moon's ocean survived and another's froze, the difference may have nothing to do with the moons themselves. It may simply reflect which of them happened to be caught in a resonance at the right moment, and for how long. These are not 5 independent experiments. They are 5 outcomes of one long shared history, and the history has never been directly observed. All of these require the same thing, a well-instrumented orbiter making repeated close passes of each moon over a period of years. A single flyby cannot do it. Flybys give you one snapshot of a varying signal, and a varying signal is precisely what the method needs to sample repeatedly. There is a reason this matters beyond the bookkeeping of which moons hold water. Where liquid water sits against rock, chemistry happens. Minerals dissolve. Elements enter solution. Energy gradients form at the boundary between the two, and gradients of that kind are what any chemistry, including the kind that matters most, has to work with. The carbonates hinted at on Ariel are the direct fingerprint of that process having occurred somewhere below. None of this establishes anything about life, and it should not be stretched to. But it does establish that the conditions people travel across the solar system to investigate elsewhere may exist here as well, 4 times over, unexamined. That orbiter has never existed. The measurement has never been attempted. It is not that the question is difficult to answer. It is that nobody has ever been in a position to ask it. And there is a consequence to that which is easy to state and hard to absorb. If 4 or 5 separate moons of Uranus each hold a layer of liquid water, then that single system contains more independent subsurface ocean environments than any other planetary system we know of, including Jupiter's and Saturn's. It would be the largest concentration of hidden water in the solar system outside the giant planets themselves. And not one of those oceans has been confirmed because nothing has ever gone there to look. Part 10. 42 Years of Night. The environment these worlds sit in is as strange as their geology, and it is driven by the same tilt that began this account. Because each pole faces the Sun for roughly 21 years, and then faces away for roughly 21, every point on every one of these moons experiences a light cycle that nothing else in the solar system comes close to matching. High latitudes receive something near 42 continuous years of dim daylight, and then something near 42 continuous years of unbroken night. Lower latitudes fare somewhat better, catching a low sun at the extremes of the cycle, but nowhere on any of these moons is there anything resembling a daily rhythm of light and dark tied to the moon's own rotation. Surface temperatures sit somewhere between 60 and 85 Kelvin, which is roughly -190 to -215 degrees Celsius. They shift slowly with the long seasons, rather than rising and falling with any daily cycle, so the thermal environment changes on a timescale of decades. A surface that is warming has been warming for years and will keep warming for years more. That has real physical consequences, and they are the reason these worlds are not quite as static as they appear. Volatile compounds on these surfaces, and particularly carbon dioxide, are mobile at these temperatures. Not liquid, not flowing, but capable of leaving the surface as gas and returning to it as frost. Over the course of a long summer, sunlight liberates them from warmed terrain. They drift in ballistic arcs, unimpeded by any atmosphere. And they refreeze wherever they encounter somewhere colder, which means the winter hemisphere and the permanently shadowed floors of craters. Then the season turns, and the process runs the other way. The result is that the surfaces of these moons are not fixed. They redistribute themselves on a 42-year rhythm, building and dismantling frost deposits over spans longer than most human careers. Bright patches migrate. Dark regions are stripped and slowly replenished. A map of one of these moons made at one point in the cycle would not perfectly match a map made half a cycle later. And we have watched perhaps half of one such cycle, from an enormous distance, through telescopes that cannot resolve surface detail without ever seeing the hemisphere where the material was going. Then there is the magnetic environment, which is genuinely peculiar, even by the standards of this system. The planet's magnetic field is not aligned with its rotation axis. It is tilted about 59 degrees away from it. And it is not centered on the planet either. It is offset from the middle by roughly a third of a planetary radius. Put those together, and what surrounds these moons is not a neat magnetic bubble with them circling politely inside it. It is a lopsided, off-center field being swung around by a planet that rotates in about 17 hours. From the perspective of a moon, the magnetosphere tumbles. The field configuration overhead changes drastically several times a day, opening and closing, strengthening and weakening, sweeping charged particles across the surface from directions that keep shifting. Those particles do work. They strike the surface with enough energy to knock atoms loose, a process called sputtering, which slowly erodes exposed ice. They break chemical bonds, splitting water molecules apart and allowing the fragments to recombine into new compounds. They manufacture carbon dioxide out of water ice and carbon-bearing material. And over very long periods, they convert simple organic material into dark, reddish, complex residues that absorb light rather than reflecting it. This is the leading explanation for why these moons are as dark as they are. It is also the explanation for why the trailing hemispheres are chemically distinct from the leading ones. The magnetosphere co-rotates with the planet faster than any of the moon's orbit, so it continually overtakes them and strikes their trailing sides preferentially. Anywhere you see a hemispheric chemical asymmetry in this system, plasma bombardment is the first suspect. The inner four moons all orbit inside the magnetosphere and receive this treatment continuously. Oberon, furthest out, spends part of each orbit outside it, which means its surface has a different processing history from the others, and that difference may be part of why it looks the way it does. There is a final complication in all of this, and it goes back to the thinness of the record. The one direct sampling of this environment was made during the flyby. Everything we believe about the plasma these moons live in, the density of it, the energy of the particles, the shape of the magnetosphere, and the way it interacts with each moon, traces back to a few hours of measurements taken by one instrument on one pass. Later reanalysis of that record suggests the spacecraft arrived during an unusually compressed state of the magnetosphere, squeezed inward by a gust of solar wind that happened to be arriving at the same time. Estimates suggest that particular configuration may hold only a few % of the time. If that reading is correct, then the single measurement underpinning 4 decades of thinking about how these surfaces are being weathered was taken on an atypical day. Not a wrong measurement, an unrepresentative one. And there is no second measurement to compare it against. The tumbling field does have one redeeming quality, and it is the same quality mentioned earlier. A strongly varying magnetic field is exactly what an induction search requires. The very feature that makes this environment difficult to model makes it unusually easy to probe, if anything were ever there to do the probing. The planet has spent 4.5 billion years running the experiment. Nobody has been present to read the result. There is another consequence of the tilt that deserves a moment, because it applies to the atmosphere of the planet as well as to the surfaces of the moons. Seasonal atmospheric collapse is a documented phenomenon elsewhere in the outer solar system. A thin atmosphere freezes out onto the winter hemisphere as temperatures fall, and returns to the gas phase when the sun comes back. On these moons, where any atmosphere is measured in traces rather than in pressure, the same process operates on whatever vapor exists. Titania's faint carbon dioxide signature may be the visible edge of exactly that cycle, a whisper of gas that has been condensing and evaporating on a 42-year clock since long before there was anyone to measure it. And there is one more effect that has no analog in ordinary experience. On an airless surface, bathed in plasma, dust grains acquire electric charge. Like charges repel, and on a world where gravity is measured in fractions of a % of Earth's, that repulsion can be enough to lift fine particles off the ground entirely. Dust can float above these surfaces, suspended, drifting slowly, held up by electrostatic forces rather than by any wind. It is one of the few things in this system that moves quickly enough for a human observer to notice, and it moves for reasons that have nothing to do with air. It is worth adding one calibration to all of this, because the word darkness has been doing a lot of work. Sunlight at Uranus is about 1/400th of its intensity at Earth, which sounds like night. It is not. It is still roughly 1,000 times brighter than a full moon on Earth. Daylight on these surfaces would be perfectly adequate for seeing. It would look like a very deep twilight, the light of an hour after sunset, holding steady for 21 years. The night, when it comes, is a different matter. With the sun below the horizon for 4 decades, the only illumination on a winter hemisphere would be starlight, the faint glow of the planet itself where it is visible, and whatever light the other moons return. On the far side of a moon, where the planet never rises, there would be nothing but stars. And permanently shadowed crater floors near the poles never receive direct sunlight even at the height of a 21-year summer. Those places have been in darkness continuously since the moons formed. Whatever has drifted into them over the long history of the system has been sitting there, undisturbed and entirely unlit, for something close to 4.5 billion years. Part 11. What it would be like to stand there. It is worth translating the numbers into experience, because the physical conditions on these moons are unlike anywhere a person has stood, and unlike most of the places people imagine standing. Start with weight. On Miranda, surface gravity is about 8/1000ths of Earth's. A person who weighs 70 kilograms here would register something in the region of half a kilogram there. That is not weightlessness, but it is close enough that ordinary movement becomes a problem of restraint rather than of effort. A casual step, taken with the force a human body applies without thinking, would launch you. A deliberate jump could carry you tens of meters, and the descent would take a long, slow while. Walking, in the sense of a controlled sequence of falls forward caught by the next foot, would not work at all. Movement would be a matter of pushing gently off and waiting to arrive. Ariel is more forgiving, at roughly 27/1000ths of Earth's gravity, and Titania and Oberon are more forgiving again, but nowhere in this system does anything feel remotely like weight as the body understands it. Escape velocity from Miranda is only about 190 meters per second. That is beyond human strength, so you could not throw yourself off the moon. But it is low enough that a thrown object follows a visibly curved arc for kilometers before it lands, and low enough that impacts routinely fling material clear of the moon entirely, never to return. Then there is the light. At 19 or 20 times Earth's distance from the Sun, sunlight arrives at about 1/400th of the intensity we are used to. As established, that is not darkness. It is on the order of 1,000 times brighter than a full moon on Earth, which is enough to see terrain clearly and enough to read by. But it does not look like our daylight, and the reason is the Sun itself. At that distance, the Sun is no longer a disk. It is a point. Brilliant, painful to look at, but geometrically a point of light in a black sky. And a point source casts shadows with perfectly hard edges. There is no atmosphere to scatter light around obstacles, no softening at the boundary between lit and unlit ground, no ambient glow filling in the dark side of a boulder. Everything is either fully illuminated or completely black, with nothing in between. The landscape would look like a photograph taken with a single harsh flash, holding still for 21 years. The sky is where it becomes genuinely disorienting. Every one of these moons is tidally locked, which means the planet does not rise and does not set. It hangs in one fixed position in the sky, in exactly the same spot, for as long as you stand there. Not for a night. Not for a season. For as long as anyone stands there, ever, and for as long as anyone will. From Miranda's surface, the planet spans roughly 22 degrees of sky. That is about 40 times the width of the full moon as seen from Earth. It is a wall. A pale blue-green surface filling a substantial fraction of the view, its cloud bands faint and almost featureless, its color coming from methane in the upper atmosphere, absorbing the red end of the spectrum and returning the rest. It does not move. It does not change much. It goes through phases as the moon orbits, so it can be a full disk, or a crescent, or a dark circle blocking the stars, but it stays in place while it does so. From Oberon, further out, the planet is smaller, but still about 5 degrees across, roughly 10 times the width of the full moon from Earth. Still fixed. Still silent. And from the far side of any of these moons, the planet is not visible at all. It never has been, and it never will be, from that hemisphere. There is a permanent half of every one of these worlds from which the world they orbit cannot be seen. The rings would be visible from the inner moons, seen nearly edge-on because the moons share the planet's equatorial plane. They are thin and very dark, so they would appear as fine lines rather than as the broad, bright arcs Saturn's rings present. And the other major moons would be there too, bright points and small disks, moving perceptibly over the course of hours, the only things in the sky that visibly change. Add the silence, which is absolute. No air means no sound at all. Nothing carries. A rockfall 100 meters away would happen in complete quiet. Add the cold, which is not merely low temperature but a continuous drain. In vacuum, heat leaves an object by radiation alone, steadily, without pause. Anything warm on these surfaces is losing heat continuously to a sky at nearly absolute zero and must generate replacement heat forever or stop being warm. Add the horizon. On a body 470 kilometers across, the surface curves away close enough that the curvature is directly visible. The horizon would sit only a few kilometers off, noticeably rounded, and things would disappear over it quickly. And then add the season. If you arrived at the wrong point in the cycle, you would watch the sun go down. And it would not come back for 4 decades. Not dimmer light, not a long dusk. The sun below the horizon, the stars fixed overhead, the planet hanging exactly where it always hangs, and 42 years of that before anything changes. It is worth returning to Verona Rupace with all of this in place, because the cliff makes a different kind of sense once the setting is filled in. Standing at the top of it, you would be looking down a wall somewhere between 5 and 20 kilometers high, lit by a point source that casts absolute black shadows, under a sky where a pale blue-green planet fills a quarter of the view and never moves. The base of the cliff would be in shadow or in light depending on the angle, with no gradient between the two. There would be no sound, no wind, no dust in the air to give the distance away. Depth perception would be difficult because everything is either sharply lit or invisible, and there is no atmospheric haze to tell your eye how far away anything is. And the drop itself would not read as dangerous to any instinct a human body carries. At 8/1000ths of a gravity, stepping off would feel like stepping into water. The fall would begin so gently that the first several seconds would barely register as falling. Every reflex that keeps a person back from an edge is calibrated to Earth, and every one of them would give the wrong answer. That is a useful summary of the whole system, in the end. Nothing there is fast. Nothing there announces itself. But the lethal parts are lethal by accumulation rather than by force, and the instincts that keep people alive on a warm, heavy planet are precisely the instincts that would fail out there. Nothing about this environment is dramatic in the moment. That is what makes it worth describing carefully. There is no storm, no violence, no hazard that announces itself. It is simply, quietly, arranged in such a way that a human being has no place in it at all. Every element of it, the gravity, the light, the temperature, the silence, the length of the night, sits far outside the narrow band of conditions a body evolved on a warm, heavy, noisy planet can tolerate. There is one exception to all of that stillness, and it belongs to the sky rather than the ground. From the inner moons, the other members of the family would be genuinely worth watching. Miranda completes an orbit in a day and a half, Ariel in 2.5 days. Seen from one another, they would move visibly against the stars, brightening and dimming through their phases, occasionally passing in front of the planet as small dark disks, crossing that enormous pale face. On a world where nothing else changes for decades, the moons would be the only clock. And it has been like that, unchanged in any essential way, for 4.5 billion years. Part 12. Why we have not gone back. The obvious question, given everything described so far, is why no spacecraft has returned in 4 decades. The answer is a chain of practical constraints, none of them insurmountable on its own, all of them expensive, when taken together. Distance is the first of them. Uranus sits around 19 to 20 times as far from the Sun as Earth does. That is not a small step beyond Jupiter and Saturn. It is roughly twice the distance to Saturn, in a region where the Sun provides 1/400th of the energy it provides here. Radio signals take roughly 2.5 to 3 hours to cross that gap in one direction. Nothing there can be flown interactively. Every command is a prediction about a situation that will exist hours after the command was written, and every response is a report about something that has already finished happening. A spacecraft at Uranus has to be capable of managing itself, because there is no possibility of anyone on Earth intervening in time. Power is the second constraint, and it follows directly from the light levels. Solar panels are impractical at 1/400th of Earth's sunlight. You would need an implausibly large array to run a serious instrument suite. So any mission out there requires a radioisotope power source, which is a limited resource, expensive to produce, and subject to its own supply constraints. Getting useful mass out that far is the third. It requires either a very large launch vehicle or a gravity assist, and the assist that works best is Jupiter's. Mission studies have identified strong launch opportunities in the early part of the coming decade that use a Jupiter swing-by and take roughly 13 years in cruise. Without Jupiter, the routes still exist, running through Venus and Earth flybys instead, but they cost additional years of travel, or they reduce how much hardware actually arrives, or both. The Jupiter geometry is the constraint that bites hardest, because it does not persist. The alignment that makes an efficient Jupiter-assisted trajectory to Uranus possible recurs on a cycle of roughly a dozen years. A missed window is therefore not a delay of months. It is a delay of more than a decade, before a cruise that itself lasts more than a decade. A mission approved late is a mission whose data arrives a generation later than it might have. And that is before considering the human timescale involved. A mission that launches, cruises for 13 years, and then operates in orbit for several more means, results arriving something like 2 decades after approval. The people who design these missions are frequently not the people who receive the data. That is a real feature of outer solar system exploration, and it shapes how such missions are advocated for and how they are funded. Then there is the argument that has nothing to do with engineering at all, and it is the one that gives this whole subject its deadline. The northern hemispheres of these moons, the halves that have never been photographed by anything, are rotating into sunlight now. The system is moving through its long northern spring and on toward northern summer, and over the coming decades, those faces will be lit for the first time since anyone has had the instruments to look at them. A spacecraft arriving in that window could map the unseen halves of 5 worlds. It could resolve whether Miranda's coronae are 3 provinces or 20. It could establish whether Titania's fracture system is regional or global. It could photograph the far side of Umbriel and find out whether Wunder's bright ring is unique or one of many. It could complete the first global maps of bodies that have been known for centuries. A spacecraft arriving late would find those same faces sliding back into darkness. And the wait would not be a matter of years. It would be a season measured in decades, which no realistic mission would sit through. The practical opportunity to complete the map of these worlds is therefore not open-ended. It is a window measured in decades, and the next comparable one does not arrive for most of a century. That is the single strongest reason a Uranus mission has been ranked at the top of the priority list for the current decade. Not because these moons are the most likely places in the solar system to hold life. Not because the planet is the most spectacular target, but because the lighting is right now, and it will not be right again for a very long time, and everything else about the case, the possible oceans, the unexplained geology, the fact that the ice giants as a class are the least understood major planets in the solar system, arrives on top of that timing. The mission that has been studied would carry an orbiter and an atmospheric entry probe. The probe would be dropped into the planet's atmosphere to measure its composition directly, which constrains how the whole system formed and how the ice giants fit into the history of the solar system. The orbiter would spend years making repeated close passes of the moons, building exactly the magnetic induction dataset the ocean question requires, mapping the surfaces at resolutions orders of magnitude better than the flyby managed, with cameras that work at light levels the older system could not handle. None of that is speculative technology. It is ordinary planetary science hardware, of a kind that has flown many times. The obstacles are budget, launch windows, and the sheer patience the outer solar system demands of anyone who wants to look at it. It is worth being clear about what a modern instrument would actually gain, because the improvement is not incremental. The flyby's best resolution on Miranda was a few hundred meters per pixel, and on the other 4 moons it was kilometers. A modern camera in orbit, passing close, would resolve features a few meters across. That is the difference between seeing that a valley floor is smooth and seeing the individual flow fronts within it. It is the difference between knowing a cliff is somewhere between 5 and 20 kilometers high and measuring it to within a few meters. Every question raised in this account, what the coronae are, whether the chasma floors were flooded, what the bright ring on Wunda is made of, what the mountain on Oberon's limb belongs to, is a question that better images would simply answer. There is also the matter of competition, which is not a scientific consideration, but is a decisive one. The same launch windows that suit Uranus also suit other outer solar system destinations, and proposals for those destinations are strong. Saturn's moon Enceladus, with its confirmed plume and confirmed ocean, is an obvious rival. Jupiter's moon Europa has missions already flying. Mars consumes an enormous share of planetary budgets on its own. Each of these is a good target, argued for by serious people, and the total available funding does not stretch to all of them at once. A Uranus mission has to win that argument in a specific decade, against specific rivals, with a specific launch window that closes. And it is worth acknowledging what is being weighed. Enceladus and Europa offer a confirmed ocean and a plausible path to sampling it. Uranus offers 4 or 5 possible oceans, none confirmed, around a planet that is itself the least understood major body in the solar system, at twice the distance and with a decade of additional cruise. It is a harder sell, and it has been made harder every time it has been deferred. Smaller and cheaper concepts have been examined as fallbacks, including flyby-only missions that would pass through the system without stopping. They would return far better images than we currently have. But a flyby cannot make repeated passes, and repeated passes are what an ocean search needs. A single crossing of a varying magnetic field gives you one sample of a signal that has to be measured many times to be understood. So the position is this. The measurement is well defined. The hardware is understood. The trajectory is worked out. The scientific case has been made and accepted. And the lighting, after 4 decades of darkness, is finally about to be right. Part 13. The half we have never seen. What makes the moons of Uranus unsettling, in the end, is not any single feature among them. It is the ratio between how little has been looked at and how much that little turned out to contain. Consider carefully what one partial hemisphere each imaged once at coarse resolution 4 decades ago by a spacecraft that could not stop and was not designed for the task, actually produced. The tallest cliff known anywhere in the solar system, a wall of ice somewhere between 5 and 20 kilometers high, on a moon 470 kilometers across, down which a fall would take 12 minutes. 3 provinces of banded terrain that exist nowhere else, with edges so sharp they look drawn, on a body that should have been geologically finished before the first cells appeared on Earth. Modeling built on those same images which concludes that this small moon once held an ocean occupying half its volume within the last few 100 million years, set against equally careful modeling which concludes it could never have held one at all. A moon whose valleys appear to have been flooded from below by something cold and thick, and whose surface is currently exhaling a gas that should have vanished from it long ago, which means something is still supplying it. A crater floor, carrying the only bright feature on the darkest moon in the system, seen once, obliquely, at the very edge of the light, and never seen again. A fracture running 1,500 kilometers across the largest moon, of exactly the kind an ocean leaves behind when it freezes. A mountain roughly 11 kilometers high, taller than Everest, caught in profile against black sky in a single frame, its nature entirely unknown because it was never seen from any other angle. And the conclusion, drawn from all of it together, that 4 and possibly 5 of these worlds hold or once held liquid water beneath their crusts, which would make this system the largest concentration of hidden oceans anywhere we know of outside the giant planets themselves. That is the yield from the half we could see. The other half of every one of these worlds has never had a photon of sunlight recorded from it by any instrument humanity has ever built. Not a low-resolution image. Not a partial map. Not a smudge. Nothing at all. It is worth being precise about this because it is the sort of statement that sounds like exaggeration and is not. There are 5 planetary bodies orbiting the 7th planet, ranging from 470 to over 1,500 kilometers across. Half of every one of them is unobserved. Whatever is written on those surfaces, whatever craters, whatever fractures, whatever provinces of terrain that have no counterpart on the observed side, has never been seen by anyone. Modern maps of these moons mark the region as blank or fill it with interpolation, which is an unusual thing to encounter in a planetary atlas in this era, when nearly everything else of comparable size has been mapped globally at least once. And the inventory itself is not finished either. Small moons are still being found in this system with modern telescopes, including one only about 10 kilometers across that the flyby missed entirely, which is a reminder that the question is not merely how well we have mapped what is there. It is partly still a question of what is there. The unimaged hemispheres are not blank in reality. They are only blank to us. They may contain additional coronae, which would change how the Miranda story is read entirely. They may contain compressional features of the kind a freezing ocean leaves behind, which would settle an argument that has been running for years. They may contain bright deposits like wunders, which would strengthen the cold trap explanation considerably, or contain none, which would weaken it. Every one of those is a real, testable prediction, waiting on the simple matter of a camera being pointed in the right direction at a time when there is light to see by. It is worth noting how unusual that situation is by the standards of modern planetary science. Mercury has been mapped globally. Venus has been mapped globally through its clouds by radar. The Moon has been mapped to a resolution of meters. Mars has been mapped so thoroughly that individual boulders are catalogued. Every large moon of Jupiter and Saturn has been imaged from orbit, most of them repeatedly, many of them across multiple seasons. Even Pluto, at the far edge of everything, received a full encounter from a spacecraft built specifically to study it. The 5 major moons of Uranus are the exception. They are the last large bodies in the solar system that remain half unseen, and the reason is nothing more complicated than an accident of geometry. Their planet was tipped over long before anyone existed to send a camera, and the one camera that ever passed arrived in the wrong season. Everything we believe about them, therefore, comes from a mission that was not designed to study them, could not stop for them, and photographed them at whatever angle the trajectory happened to allow while on its way somewhere else. It is a remarkable amount of knowledge to have extracted from those circumstances. It is also a foundation thin enough that a single well-planned mission could overturn substantial parts of it. That word, fear, is worth examining, since the framing of this account has leaned on it throughout. These worlds are not dangerous in any way that will ever matter to anyone listening. Nothing on them threatens anything. The unease they produce is not physical. It is the unease of an enormous gap in the record, sitting quietly inside a solar system we generally speak about as though we have surveyed it. We have not surveyed it. We have surveyed most of it, and left 5 worlds half seen and moved on. And it is not a permanent condition, which is the part that gives the whole subject its weight. Those hidden hemispheres are turning slowly into the light right now. Not metaphorically. The system is moving through its long northern season, and the faces that have been dark since before anyone had the instruments to look at them are coming into sunlight over the coming decades. It is a window, and it is measured in decades rather than in centuries, and when it closes, the same faces slide back into a night of comparable length. What is written on those surfaces has been written for a very long time. Whatever happened on the far side of Miranda happened hundreds of millions of years ago and finished. Whatever fractures cross the northern half of Titania have been there since before anything on Earth had a spine. The record is not going anywhere. It will still be there long after we are finished wondering about it, and it will still be legible to whoever eventually arrives with something capable of reading it. Whether anyone is in a position to look while the light is on is a much smaller question than the one those surfaces answer, and a much more temporary one. The moons are indifferent to it. They have kept their record through 4.5 billion years of darkness and light, 42 years at a time, turning on their sides around a planet that lies on its side, and they will keep it whether or not anyone ever comes. There is a particular kind of peace in a thing that waits that patiently. Nothing out there is in a hurry. Nothing out there needs us to arrive. The cliff on Miranda will stand whether it is measured or not. The ring on Wunder's floor will keep collecting whatever drifts into it. The oceans, if they are there, will go on being there, cold and dark and undisturbed, beneath 100 kilometers of ice, in a silence that has never once been broken. And the far sides of those 5 worlds are turning slowly into the light, on a schedule that has nothing at all to do with us. Let your breathing slow. Let the dark settle around you. Sleep well and good night.